strategic architecture of modern airspace control has fundamentally shifted from a paradigm of kinetic endurance to one of electromagnetic and algorithmic supremacy. For decades, the global understanding of integrated air defense systems, particularly those developed within the Eastern military doctrine, was predicated on the concept of anti-access and area denial. These systems, utilizing multi-layered radar arrays operating across various frequency bands, were designed to create comprehensive envelopes of risk that would render hostile aerial penetration prohibitively costly. The operational philosophy was robust: detect early, track continuously, and saturate the airspace with high-velocity interceptors. For a substantial period, this approach maintained a delicate balance of power, forcing theoretical adversaries to invest heavily in low-observable technologies and standoff munitions. However, the true vulnerability of such deeply integrated defense networks lay not in the physical interception capabilities of their missiles, but in the cognitive processing speed and data fidelity of their command and control nodes. The advent of highly specialized, low-profile tactical deployment systems designed specifically to operate within the gaps of these radar networks has altered the calculus of modern deterrence. This development represents a qualitative leap in electronic warfare and precise kinetic delivery, one that was intentionally kept away from public observation and standard intelligence assessments to preserve its operational efficacy. The primary objective of such a system is not merely the destruction of assets, but the total disruption of situational awareness, rendering sophisticated defense networks functionally blind before they can initiate a countermeasure sequence. To understand the magnitude of this technological divergence, one must examine the baseline capabilities of traditional air defense networks that dominated the late 20th and early 21st centuries. These networks relied heavily on long-range surveillance radars capable of emitting high-energy signals to detect incoming objects at extreme distances. Once a potential vector was identified, target engagement radars operating in narrower, more precise frequencies would take over, guiding interceptors to their targets. The entire infrastructure was built on the assumption that an adversary would attempt to either overwhelm the system numerically or bypass it through extreme altitude or speed. Consequently, the defense networks evolved to become exceptionally proficient at tracking traditional cross-sections, even those utilizing early iteration low-observable geometries. What the architecture did not fully anticipate was a systemic vector that could exploit the digitized data streams linking these disparate radar units. Modern defense is entirely dependent on network-centric warfare, where information from a forward radar station is processed, filtered, and transmitted to a central command node, which then designates targeting data to specific missile batteries. If this data pipeline can be manipulated, intercepted, or quietly simulated, the physical capabilities of the missiles themselves become irrelevant. The weapon system in question was engineered precisely to exploit this digital dependency, acting as a disruptive catalyst within the very communication channels that modern defense networks rely upon to function. The developmental trajectory of this specialized capability remained one of the most closely guarded initiatives within Western defense frameworks. Unlike highly visible programs involving strategic bombers or aircraft carriers, which serve as overt instruments of political signaling, this project was designed for complete anonymity. The operational philosophy dictated that the mere knowledge of such a capability would prompt an immediate and comprehensive overhaul of Eastern encryption and radar processing algorithms, thereby neutralizing the advantage before it could ever be deployed. Financial allocations were distributed across disparate, nondescript lines of research, masked as routine upgrades to existing electronic countermeasure pods or standard communication infrastructure. Engineers and software architects worked in isolated environments, developing unique waveform modulations and automated flight paths that could mimic atmospheric noise or civilian transponders with absolute precision. The physical component of the system, the delivery vehicle itself, was designed to be modular, capable of being launched from standard tactical platforms already in service, thereby avoiding the telltale signature of a new, dedicated deployment asset. This integration into existing logistics chains ensured that the system could be positioned close to critical regions, without generating the geopolitical friction typically associated with the movement of strategic assets. As regional tensions intensified and the deployment of advanced anti-access systems reached a critical density along strategic frontiers, the operational realities began to shift. The theoretical models established in laboratory environments faced the ultimate test against active, real-world sensor arrays that were continuously scanning the horizon. The presence of these dense radar envelopes created a stabilizing illusion of invulnerability for those who commanded them, leading to a rigid adherence to established doctrine. This rigidity became the optimal operating environment for the new system. When active evaluation became necessary due to shifting security dynamics, the deployment did not mirror the traditional escalatory patterns of conventional military operations. There were no mass forward movements of troops or highly visible logistical buildups. Instead, the implementation occurred with absolute discretion, utilizing specialized transport and localized deployment protocols that bypassed standard satellite observation metrics. The objective was to embed the capability within existing defensive postures, creating a latent deterrent that could be activated instantaneously if the established balance of power was critically threatened. The technical operational mechanism of this system represents a departure from traditional electronic jamming. Conventional jamming relies on brute force power, emitting high-intensity signals to flood an enemy radar screen with noise, effectively blinding it, but also alerting the operator to the exact presence and direction of the jammer. The advanced system utilizes a methodology of digital radio frequency memory and cognitive electronic manipulation. Instead of blinding the radar, it intercepts the incoming radar pulse, alters its characteristics, and sends it back to the receiver. To the radar operator or the automated tracking algorithm on the other side, the return signal appears completely legitimate, but it describes an empty airspace, a completely different flight path, or a multitude of false targets scattered across the display. This creates a state of profound data corruption within the enemy command structure. Decisions are made based on information that appears mathematically sound, but is entirely fabricated by the intruding system. By the time the discrepancy between the digital display and physical reality is recognized, the window for effective interception has closed, allowing Allied assets to operate with unprecedented freedom within zones previously considered entirely inaccessible. Furthermore, the physical characteristics of the delivery vehicle are optimized for low probability of detection, utilizing advanced composite materials that absorb electromagnetic radiation rather than reflecting it. The airframe minimizes its physical signature across multiple spectrums. The propulsion system is engineered to minimize thermal emissions, preventing infrared-based tracking systems from establishing a reliable lock. Operating at altitudes and profiles that exploit the terrain masking capabilities of regional geography, the system moves beneath the effective horizon of long-range surveillance assets. When combined with its electronic manipulation suite, the vehicle becomes effectively invisible, moving through dense sensor webs not by breaking through them by force, but by weaving through the digital tolerances built into their programming. This seamless integration of physical low observability and digital deception defines the new standard of strategic penetration. The implications of this capability extending into the operational theater have fundamentally challenged long-held military doctrines regarding area denial. For a considerable duration, tactical planners operated under the assumption that entering a contested airspace required a prolonged, resource-intensive campaign to physically destroy radar installations and missile launchers using standoff weapons. This approach required immense logistical support and guaranteed a high level of visibility, signaling intent long before the primary objectives could be achieved. The introduction of a specialized, low-profile manipulation system introduces an alternative methodology: temporary, localized neutralization. By disrupting the sensor network exactly when and where it is required, the system creates transient corridors of safety through which tactical operations can be conducted with minimal risk. Once the operation is complete, the system can cease its manipulation, leaving the defense network seemingly intact but functionally compromised, leaving the operators unaware of the breach until a post-operational analysis is conducted. This shift in capability has a profound psychological effect on command structures that have historically relied on the absolute certainty of their defensive barriers. When a defense system that has been marketed and trusted as impenetrable fails to register an intrusion, or worse, processes the intrusion as normal activity, the entire chain of command experiences a crisis of confidence. Every piece of data becomes suspect. Every radar return must be verified through secondary, often slower, methods of communication. This slows the decision-making cycle from seconds to minutes, an eternity in modern high-velocity conflicts. The organizational friction generated by this uncertainty is often as valuable as the physical destruction of the assets themselves, paralyzed by the inability to distinguish between reality and systemic manipulation. The strict confidentiality surrounding this program was maintained through an intricate framework of operational security that extended from the manufacturing facilities to the frontline personnel. Unlike conventional weapon systems where operators receive comprehensive training manuals and technical documentation distributed across various commands, knowledge of this system was heavily compartmentalized. Only a highly restricted group of strategic planners and specialized technicians understood the full scope of the system's capabilities and software architecture. Frontline units utilizing the component modules were often provided with specific, limited execution protocols, treating the asset as a standard auxiliary system without insight into the advanced algorithms driving its success. This design prevented unauthorized dissemination of technical specifications and ensured that even if an individual component were compromised, the core operational logic remained secure within protected repositories. The revelation of such a system's existence, even through indirect observation or unexpected performance anomalies in the field, alters the geopolitical landscape. It forces a reassessment of strategic calculations among global powers, demonstrating that technological superiority is not merely a matter of missile range or radar power, but of algorithmic agility and information control. The balance of power is no longer dictated solely by the visible accumulation of military hardware along a border, but by the invisible capabilities hidden within the software code and electromagnetic spectrum of specialized deployment systems. As modern defense frameworks continue to evolve toward total digitization, the significance of these hidden capabilities will only increase, defining the parameters of security and deterrence in an era where the most critical engagements occur within the unseen domains of data and electronic consciousness. The operational deployment and subsequent real-world integration of this advanced electromagnetic system marked a critical turning point in the management of highly contested airspace. To fully comprehend the systemic failure of established defensive doctrines, one must analyze the precise moment when theoretical vulnerability transformed into tangible operational paralysis. When advanced sensor networks, previously considered the absolute standard of regional security, were subjected to this localized cognitive manipulation, the breakdown occurred not at the mechanical level, but within the data aggregation layers. Traditional air defense frameworks operate on the principle of correlation, meaning that multiple radar stations operating at different geographic points must cross-reference their returns to validate the speed, altitude, and trajectory of an incoming object. The specialized Western system targeted this exact cross-referencing mechanism. By capturing the initial probing pulses of long-range surveillance arrays, the system calculated the exact timing required to return a slightly altered data packet to each individual receiving station. Consequently, the central command node received contradictory information. One radar reported a clear sector, another registered a low-velocity atmospheric anomaly, while a third detected a cluster of multiple decoys moving in an entirely different direction. The automated threat evaluation algorithms, unable to resolve these massive mathematical discrepancies, defaulted to an error filtering state, effectively erasing the true vector from the operational map. This methodology of localized neutralization bypassed the need for traditional kinetic suppression of enemy air defenses, which historically relied on heavy anti-radiation missiles designed to home in on radar emissions. Kinetic suppression is inherently noisy, visually obvious, and carries a significant risk of collateral friction, which can rapidly accelerate a localized crisis into a broader conflict. By contrast, the application of digital radio frequency memory manipulation allowed for the creation of transient, invisible corridors through which friendly transport and reconnaissance assets could pass without triggering automated engagement protocols. The operators sitting inside the mobile radar cabins observed nothing unusual on their main displays. The system diagnostics reported optimal functioning, and the environmental noise filters remained within normal parameters. This maintenance of a false status quo is the defining characteristic of modern information supremacy. The objective is no longer to destroy the enemy's hardware, but to control the inputs that dictate how that hardware behaves, transforming a multi-billion-dollar defensive perimeter into a passive observer of its own penetration. The material composition and structural aerodynamics of the deployment vehicle played an equally vital role in maintaining this state of total deniability. Constructed from advanced carbon lattice structures, interwoven with specialized radar-absorbent matrices, the physical frame was designed to scattering electromagnetic energy away from the source transceiver. Standard low-observable platforms are typically optimized to defeat specific frequency bands, such as high-frequency tracking radars, while remaining relatively visible to low-frequency early warning arrays. This system, however, paired its physical geometry with active cancellation technologies, emitting a low-power, out-of-phase waveform that effectively neutralized the residual radar reflections that typically bounce off even the most advanced stealth coatings. Furthermore, the thermal management system utilized a closed-loop heat exchange mechanism, temporarily storing the kinetic heat generated by atmospheric friction within internal thermal sinks rather than exhausting it immediately into the surrounding air. This eliminated the distinctive thermal plume that forward-looking infrared sensors and satellite-based early warning systems rely upon to detect high-speed, low-altitude transits. Through this combination of passive structural absorption, active waveform cancellation, and strict thermal containment, the platform operated entirely beneath the threshold of actionable detection. The institutional reaction within the adversary's military establishment following the initial field anomalies was characterized by profound internal friction and systemic confusion. Because the defense network had been integrated into a rigid, top-down command structure, field commanders lacked the authority to alter radar operational modes or override automated tracking software without explicit authorization from central headquarters. When early discrepancies began to emerge between satellite reconnaissance data and ground-based radar reports, the centralized bureaucracy struggled to process the implications. The initial assumption was not that an entirely new class of electronic warfare had been introduced, but that the ground stations were experiencing severe software corruption or maintenance negligence. This led to a series of counterproductive internal audits, software reboots, and the temporary decommissioning of key radar batteries for diagnostic testing, further compromising the integrity of the airspace during critical windows of observation. The psychological impact of this systemic uncertainty cannot be overstated. When military personnel lose faith in the fidelity of their primary instruments, the entire operational tempo slows down, creating a state of functional paralysis that spreads from the radar operators up to the highest levels of strategic planning. The technical architecture driving this capability is rooted in the evolution of cognitive electronic warfare, where machine learning algorithms are embedded directly into the sensor payload of the deployment vehicle. Traditional electronic countermeasures utilize pre-programmed jamming profiles designed to disrupt specific known radar models. If the adversary introduces a new frequency hopping technique or changes their radar pulse repetition frequency, the traditional jammer becomes ineffective until it can be reprogrammed in a laboratory environment. The advanced system avoids this limitation by utilizing an onboard software-defined radio architecture capable of analyzing unfamiliar electromagnetic emissions in real time. Within milliseconds of encountering a novel radar signature, the system's cognitive processor identifies the underlying mathematical structure of the signal, predicts its next frequency shift, and generates a tailored manipulation strategy on the fly. This level of algorithmic agility ensures that the system remains effective, even against highly adaptable, modern multi-mode radars that constantly vary their operational parameters to avoid detection. The logistical integration of this capability into Western defense frameworks was executed with a level of discretion that matched its operational profile. To prevent foreign intelligence agencies from identifying the movement of a new weapon system, the components were distributed across existing, routine supply chains under standard replacement part nomenclature. The modular nature of the system allowed it to be housed within standard containers that were identical in weight, dimensions, and electronic signatures to conventional cargo. It could be mounted onto standard multi-role aircraft, unmanned aerial vehicles, or standoff naval platforms without requiring specialized modifications to the launch mechanisms or external pylons. This high degree of commonality meant that any standard deployment of conventional forces carried with it the potential latent presence of this strategic ace, forcing foreign intelligence analysts to guess whether a routine patrol was a standard exercise or a highly specialized neutralization mission. As the realities of this technological shift became apparent to global defense analysts, the broader implications for international security frameworks began to reorient. The traditional model of deterrence, which relied on the visible accumulation of massive kinetic forces along strategic boundaries, has been superseded by a more complex dynamic centered on technological asymmetry and information control. When an established power can no longer guarantee the integrity of its defensive boundaries, its ability to project political influence diminishes significantly. The multi-billion-dollar investments made into fixed, long-range anti-access networks are rendered economically and operationally non-viable when confronted by a low-profile modular system that can neutralize them at a fraction of the cost. This shift effectively reopens contested regions to international monitoring, surveillance, and tactical flexibility, fundamentally altering the calculus of regional stability and challenging the assumption that geographic isolation can be maintained through sheer numbers of missile batteries. Ultimately, the development and utilization of this secret capability underscores a fundamental truth about the nature of contemporary competition between advanced state actors. Physical hardware, the missiles, the radar dishes, the armored command bunkers, represents only the visible manifestation of military capability. The true seat of modern power resides within the unseen digital architecture that links these components together. By mastering the manipulation of this digital tissue, the advanced Western system demonstrated that information fidelity is the ultimate high ground in modern conflict. The weapon system was never supposed to be seen because its very visibility diminishes its utility. Its power lies in the quiet, unacknowledged enforcement of a technological standard that leaves the adversary searching an empty sky, entirely unaware that the balance of power has already shifted beneath their feet. As sensor technologies continue to advance, the race to control the data streams that inform them will remain the primary driver of classified defense research, ensuring that the most critical assets in any future scenario will remain completely hidden within the electromagnetic spectrum.